Good morning and good afternoon. Welcome to the DEKOMTE webinar hosted by the IMechE. I'd just like to start with a thanks to the IMechE for allowing us to have this event on their platform. I hope everyone is connected okay and can see the broadcast. This presentation is going to have a short introduction through expansion joint technology for power stations, with some emphasis on some of the new solutions DEKOMTE has created to improve the reliability of plants. The presentation is aimed to take about 45 minutes. We will then have some Q&A session. There's a number of topics which I'd really like to take everyone through. We'll have a little bit of a brief introduction to DEKOMTE, those who are not familiar with us, but we mainly want to focus on the membranes and the case studies, which should be interesting for all those folks who are involved in power stations. There's going to be a few polls that will come through the presentation. If you are able to interact with that, that'll be great. Just a few short questions which will allow us just to tailor a little bit to some of the information which we're going to present for you, so that we understand the interests of the audience today. We're also open to any questions you've got, so if during the presentation you want to just type in your questions, that would be great. We may answer some questions as we go if they're particularly applicable to a slide, but we will try and leave most questions to the end. I know this is a presentation where the interaction is limited because you're mainly all just looking at the slides and listening to me, but we really hope that you do interact a little bit with us, because we certainly would love to engage with the challenges and the issues which you guys are looking to solve. So I think we should start with who DEKOMTE is, for those of you who don't know. DEKOMTE was founded 42 years ago, and the basis of our company is offering bespoke technical solutions. We saw the gap that existed in the market for expansion joints, in that most manufacturers focused on standardized products to reduce cost. And our perspective is to actually listen to the requirements of the plant and the requirements of the OEM, and use a technological advantage to save money in the longer term by the value of the product being more reliable. That's been successful for us. We're a successful small business, around 400 people, focused only on expansion joint solutions. The products that we're involved with, we are mainly focused to fabric expansion joint technology. And when we talk about fabric expansion joints, we mean not just the membrane system, whether that be rubber, PTFE or metallic, but we also mean the complete assembly. It is the complete assembly which secures that membrane that will really give the reliability and the function of this system. We're also involved in many of the other expansion joint products, metallic bellows, PTFE expansion joints, rubber expansion joints and flexible hoses. But as I said, most of our resources and technology and engineering expertise is focused to fabric parts. We're also providing a lot of services for both OEM and aftermarket customers. Initially, this can be focused around design and investigation services, assessment, analysis. We also look to see how we can support and design of the adjacent systems, how the expansion joint, as I said in the previous slide, is really integrated into the duct system, has a significant impact on expansion joint reliability and life. For existing equipment, we provide inspection and servicing, technical expertise on site to analyze how a product can be extended in its life, rather than just waiting for failure. And the next section specifically of this presentation is going to focus on inspection and specification, as we feel that's a really key part of the puzzle. We have to get the initial question right. We need to help you get the inquiry right. We need to understand your plant correctly in order to then assist you with the right solution. And lastly, under services, we are providing turnkey installation scope. That means that we are supplying our supervisors and technical advisors together with the manpower required to carry out the complete installation work in the field. We're successful in supplying a number of industries, but our focus is very much on power generation. Our strength is in gas turbine exhaust systems and HRSG applications, but historically we have a very large reference in fossil fuel power generation, and now most of that technology pushes more towards biomass, waste to energy, incineration style plants, but as we refer to the Rankine cycle, it's a steam cycle system, which still requires the use of many expansion joints within a furnace application. There's many other types of industries we're involved in, and we list just a few of them here. So if any of those of you who are listening to this are from other industries, we'd also love to have some interaction with you, and I'm sure we can support you with some special solutions in your field. The key for us are solutions which require high temperature and higher movements. These are the ones which create the most arduous conditions for expansion joints and create those challenges of how to keep those membranes functioning for the longest period of time. The other application just to mention also on here is where there is particulate, so dust, ash, chemicals, anything that's more unusual in the medium stream also creates some significant challenges, and that pops up as well from some of these industries where we've had some unique solutions to solving those problems. So just a little bit about DEKOMTE. If anyone has any questions, they can also contact us separately. On a general note as well, I hope that some of you within this workcast system have noticed there's also some media content available. All our normal brochures are there available for you to download as well, so maybe make use of those resources a little bit later on. The next section of this presentation is, for me, really the most important one, inspection and specification. As I already said, the story always starts at the beginning. The story always starts with the right question, and we need to think about how do we support our customers to create the right question, to understand what the right scope of supply might be. And this always starts with us actually trying to understand the experiences that the customer already has. So we can do that by a visual and thermographic survey, coming onto site and discussing with you and understanding what you've got, what you've done, what you've modified, how you've changed what you originally had, what happened to what you originally had installed, to see what that complete story of issues that you've had or what you've tried. We also need to think about the extent that we're going to view on site, the scope. The membrane, of course, is the functioning part of an expansion joint. That's the part that's going to keep the gas tight and allow the flexibility. But that membrane has to be attached, and it's the attachment points, those fixing systems, which will become the weakest element. It's then the adjacent parts that cause problems. A typical one is adjacent insulation on piping systems, or adjacent insulation systems on ducts, or internally within internally insulated duct systems, liner plate and insulation systems. We see, and a case study I'm going to show a little bit later on is looking at the thermal gradients and properties within the steel frame and how that impacts the expansion joint. But adjacent duct stiffeners, adjacent flanges, any stress, cracking or fatigue that's coming from the adjacent duct parts is going to have a detrimental impact. So when we're looking at the expansion joint, in simple terms, we need to look at, for an expansion joint which is 500 millimeters or half a meter or 2 feet, we really need to be looking at over a meter or over 4 feet of scope to see what's happening around it. As a useful guide and something which we were also willing to share with those who will be interested in it, we've got some really good questionnaires which can be used to help to know what to look for when doing inspection, and also some measurement sheets and technical questionnaire which can be used for identifying all the correct parameters and correct dimensions. So some of the points which I just want to comment on here is what's the condition and the age of the expansion joint? A typical question that we get asked is how long should an expansion joint last? And I don't want to make too much of a quip of how long is a piece of string, but actually it does very much depend on what type of product is going to be installed there as to what sort of life expectancy you've got. But typically we need to think about that life of towards 10 years. That should be the goal from an expansion joint product if we have the right design and reliability. But we also need to think about the number of cycles that it's capable of. But anyway, coming back a little bit. So what's the condition of the expansion joint? What's the proximity of things around it? Airflow is particularly important. All expansion joints work on the basis of a temperature difference, and therefore ensuring that we have air circulation is quite key. Ensuring that adjacent equipment is well maintained and well insulated. We want to look at this where we say signs of movement. One of the first things that we do when we come to site is actually look at the existing drawings, the existing design spec of what was installed, and then we want to see if the duct was supposed to be moving 50 millimeters or 2 inches, actually what do we see it is moving? Because we often find that the boiler or the ductwork has moved slightly in position, we see the feet maybe aren't sliding. So reassessing what movement could be expected is also going to be a key part of re-specifying the product that's going to be necessary. And you can see some of the other points: corrosion, water damage, and of course previous modifications. And then for metallic products, it's slightly different. We have a good thermal analysis approach for fabric expansion joints. For metallic expansion joints, it requires much more a visual approach. Yeah, we need to look for signs of distortion, signs of movement which is outside the design parameters, and whether the joint is in a stressed position or not. Hopefully we'll have some information from the plant about how you're operating, so how many cycles you've currently run. And of course, very simply, you know, we want to look for physical and mechanical damage that exists. Expansion joint. Just one question that's just popped up there is someone's asked what about joints designed to absorb additional movements? Yeah, expansion joints are designed to accept a wide range of movement. So we're able to accept movements in some cases over 250 millimeters. Vibration, another concern is raised. Vibration is a particular problem for expansion joints due to the fact it's really a cycle. It's really a movement, a cycle that takes place. So we need to be very careful with vibration to understand frequency and amplitude, and then to understand what the damping mechanism that's going to be used in the piping or the assembly part of the expansion joint to make it suitable. So in principle, the answer is yes, we can design for any movement and vibration cases, but of course we need to look at again this wider scope than just the expansion joint to see what's really going on in the ducting system. I just mentioned about the operational criteria, and that's also a key point. If we talk about an expansion joint life of a number of years, it's actually much more important to equate it into a number of cycles. And you'll see in some of those case studies coming up that we're going to talk about 1,000 cycle limited solutions and 250,000 cycle limited solutions. So practically unlimited, actually, from a fossil generation facility. What we're concerned about in cycles is that not only is there a fatigue of the movement process that's going to take place, but there's also a fatigue of the temperature cycling that's going to take place. And that's not just a hot issue, that's also a cold issue. So we may also have, as we say here, acid or dew point or condensation issues which start to come into effect. So how the plant is operating is really an incredibly significant part of the specification that needs to be considered. As I already said, we have several technical questionnaires. We summarise some of the key points in this slide, but we're very happy to share with you some of the technical questionnaires and some of the measurements and data sheets, which can hopefully support if you want to compare how you are asking a supplier for expansion joint products, and maybe which data could be included to ensure that the reliability of the solution is going to improve. A final point about specification is one about standards. We're often asked, and we see the challenge with many customers, how can they compare DEKOMTE against another supplier? And the normal approach for this is, okay, ask each supplier to quote according to a specific standard requirement. The problem with fabric expansion joints is that there are very few real technical standards available. I list the three here: the RAL GZ719, European Sealing Association, and the Fluid Sealing Association. Of these three, the RAL is the only specification which actually gives technical determined criteria. The ESA and the FSA actually do refer to the RAL to try to gain some additional technical parameters. Metallic expansion joints is a little bit easier. There is an EMechE standard. Currently, the IMechE 10 is the design basis. Actually, you can go and buy this handbook or buy this program to be able to determine what the requirements of the metallic bellow will be. It only needs to be considered. Sorry, a couple of sound issues. I'll just pause. Yeah, so we just with the IMechE 10 standard, it's a really good basis to give a harmonising approach to comparing suppliers. So we definitely recommend that that's the latest standard is always requested. Okay, the next section I just want to cover is on membranes and materials. Several customers ask us about the advances in membrane materials that are available and what impact this has on expansion joint life. Yes, it is true that the membrane and the material has definitely a significance to expansion joint reliability. But I don't want to overshadow my previous comment that actually it is much more critical considering the overall assembly impacts rather than just the individual membrane. But having said that overriding point, I think it is interesting just to share with a few of you here what the differences and advancements in membranes are. I think firstly we need to understand that the membrane is going to be the temperature limiting aspect in the function of this expansion joint. So here we normally refer to a PTFE gas type membrane layer, and we're talking somewhere in the basis of 200 degrees or 400 degrees Fahrenheit, and we reduce this, as you'll see in the next couple of slides, from what the material is actually capable of, due to the fact that we have in the clamping area a real compression to seal the materials together. And in this compression and this heat trap zone, the material will be much weaker. So it's the temperature gradient in the clamping zone that needs to be really optimized for the overall solution. To compare some of the materials, in DEKOMTE we are a strong advocate of using PTFE based materials. This is not because they look the best, it's because they last in the most durable way. It's because they live up in many different conditions to the longest possible life. They also have the highest temperature resistance, so it's significantly more durable. If we talk about colder environments, then a rubber-based joint is certainly better, of which we propose between Viton, EPDM and neoprene, of which again Viton material chemically and temperature and durability wise is certainly the best. I also show it's a little bit small, but you can see it on the slide here. We can talk about a PTFE, but actually there are, even in our guide, over 20 types of PTFE materials that we can use, and actually globally there are hundreds of different types of PTFE that can be used. So just to encourage again in the specification aspect, just to refer to PTFE based expansion joint will not assure that quality is comparable between different manufacturers. We need to think about the thickness, we need to think about temperature stability, and then the surface weight and how the PTFE has been produced. And that's a little bit what I wanted to go in the next couple of slides. We've got a couple of different types of PTFE that can be used, and there is significantly different durability and different permeability that comes from these different PTFE materials. As you can see, initially from the say fluoroplastics group, FEP and PFA are the lower cousins, with PTFE being the more stable. And then if we look at different types of manufactured PTFE, we should compare a skived film, a cast film, or an extruded film, and then I put it as a separate aspect of the table here, but PTFE cross film, which is made up of many layers of PTFE over laminated in order to create a much stronger, higher temperature resistant PTFE material. So not all PTFEs are equal, and I think some awareness needs to be there that you know how to compare these. So I'd just like to now go into the case studies. We've got a number of case studies. These case studies are just a highlight, let's say. You know, this webinar is limited on time, just to give you a little bit of a taste of some of these solutions. We'll be happy to organise additional webinars or additional presentations to go in much more detail on any one of these solutions. So please save some questions for us if you want some more detail. I just want to show the diagram of 4 different types of plant. We've got a combined cycle power generation plant with the gas turbine and HRSG. Our first case study we're going to look at is on the GT exhaust. The second case study we're going to look at is the penetration seals, which are on the floor and the roof of the HRSG. The next solution we're going to look at is on a conventional boiler plant, and what we call the ash hopper expansion joint, the expansion joint connecting the bottom of the boiler to the ash conveyor system. Additional type of case studies we could present, but we're not presenting this time, is on fluidized bed boilers, particularly on the downcomer from the cyclone. We've got some special air sealing expansion joints. But the fourth case study we're going to present today is on a waste to energy plant, looking at the boiler to grate connection. So it's a little bit similar to the ash hopper, but in a waste to energy, where we're connecting to the grate under the furnace. There's also a critical application I'd like to share a few slides about. So let's start with the GT exhaust. To have a little bit of a standard view, first of all, on what type of solutions exist, I just want to show this slide where we compare 3 solutions that DEKOMTE has provided many units of over the history. The first we call our base load solution. That's the traditional style expansion joint for a hot cased externally insulated duct. And the key point of this solution is the low number of cycles you'll see. Depending on the geometry of the duct, whether it's round or square, and the cross-sectional size, those number of cycles could be anything between 250 and 500, but in any case, it's the lowest cycle limited solution. And that cycling limited solution is really based on the geometry of the frame. We've got a hot duct situation, and we've got the cold clamping area, and the temperature gradient, which is taken up the upstand section of the expansion joint, is that fatigue limiting aspect of this design. So the primary failure mode in the traditional style expansion joint is stress fatigue cracking against the upstand frame in its connection to the duct. A secondary failure mode of this expansion joint is the compression of the internal insulation bolster. As cycles take place, this insulation material that's traditionally used as a static element becomes compressed and allows a gap to form at the edge of the frame, which starts to overheat the fabric. So we see the failure mode everyone looks at is that the expansion joint is burning or failing, but the real primary cause is cracking of the steel frame, and the secondary cause is normally insulation damage. The flexing solution looks to address that by firstly staggering that upstand. So instead of having one vertical upstand with a full temperature gradient, we now have a split upstand with the temperature gradient taken across the longitudinal section. So that improves the flexibility of the frame by reducing the stress in the hot portion of the frame. In this case, we show a split fabric, so a very high movement joint, which also allows for a formed pillow system, which gives then a greater flexibility also and less deformation that's going to be caused by the insulation and the fabric elements. The third solution we show here is what we call our W frame system. And with the W frame system, there is a very small temperature gradient because the temperature gradient is only going to be across the thickness of the steel frame. And then the insulation parts, you can see we have one formed insulation part on the outside, so it formed for the shape of the movement, so no creasing or folding will occur to get the maximum cycles. And the internal insulation is split so that during a cold state it's separated, during a hot state it's coming in contact with each other. This system adds some complexity because in order to solve the primary and secondary failure modes, we now need a much more durable fabric solution, and we also need a convector system to manage the heat path through the studs and maintain, as we showed on the previous slides, that less than 200 degrees for the durability of the PTFE material. So the key point in these is that if we need more cycles, actually the first thing that's really changing is the whole steel frame assembly. This design needs to significantly change. Just to show a few examples of that in place, square ducts are the worst because the corner acts as the stress concentrating point where the frame cannot rotate or buckle to relieve its stress. And you can see on the burnt portion of the expansion joint on the photo there that the heat is coming up from the inside of the frame as the deformation of that pillow is also showing. So lots of cracking. Lots of heat damage causing the failure of these expansion joints. In that case study, we show a W frame system which was installed. So we cut out the existing flanges of the duct as well, because we realise in this case that the adjacent flanges of the duct and the adjacent stiffeners on the duct are also exacerbating that issue of stress raising by the thermal gradient. So we've looked to really integrate the frame to the duct, and we've changed the stiffening system on the duct in order that the expansion joint frame is effectively the stiffener, and that's managing that temperature profile and reducing that stress in its own frame to allow for the maximum number of cycles. The whole system was supplied and installed by DEKOMTE. And we also improved the adjacent duct insulation and obviously replace all the soft goods inside the expansion joint scope. Another solution on GT exhaust is just to touch on a hot to cold transition, because in most gas turbine exhaust systems it's the expansion joint which makes that migration from the gas turbine exhaust diffuser, which is externally insulated, and the boiler side, which is internally insulated. And so there we need a different type of expansion joint system where the inlet frame, we address the steel frame issues of fatigue, stress and temperature gradients, And on the outlet side, we address the issues of insulation integration and liner plate integration. In the outlet side, where there's internal insulation and liner plates, very often the problems are caused by just too many interfaces at the same location as the flange, as the expansion joint frame. And so integrating that adjacent part is the key to ensuring maximum life of the expansion joint. Second case study I just want to then touch on is penetration seals. Penetration seals are the most prevalent expansion joint type in a combined cycle plant. Anything from 30 to 80 of these on the floor, roof and side walls of the HRSG. Every steam pipe that penetrates through the casing wall needs to be sealed to the casing wall itself. We're supplying OEM and retrofit solutions, and for the OEM, the main choices are metallic bellows, packing glands, mechanical seals, or fabric expansion joints. We only supply gas-type solutions, so we only focus on fabric and metallic bellows, which we supply both as an OEM. The choice of which one to supply, we're often asked this question, which we think is best. And the real answer is it depends on the location of the HRSG, because actually they all have their right location. For the high movement positions, we recommend always fabric because it's the most compact way to take the biggest movement. For the roof locations or low movement locations, metallic bellows are certainly the most durable, long life solution. Very often, though, the HRSG OEM have their own preference of what they have done for many years, and therefore we normally have to follow the recommendation or the desires of the HRSG OEM. When it comes to retrofit, though, the story is a little bit different. We are strong advocates that fabric is the best solution for retrofit. That's because it's the simplest, maintainable and retrofit solution to get a gas-tight approach. For a metallic bellow to be retrofitted, you either need to deliver the bellow in a clamshell as two split halves, or you need to cut the steam pipe. Both are not good. Fabrics offer the greatest flexibility, so when we talked about specification, I highlighted the concern about re-evaluating movement characteristics. And with these small seals, movements are really important, and therefore having a bit of extra flexibility for the movement, which a fabric can offer, gives a significant advantage over retrofitting a metallic bellow. And if a bellow was delivered in split halves, consider the fact that it will be stiffer and less flexible than your original bellow. So if the original bellow failed because it wasn't flexible enough, let's not install something that's even less flexible. To look at a fabric retrofit and what does it look like, we've got a short animation here for this solution. We supply a collar which attaches to the boiler casing, a collar which attaches to the existing poison pad of the pipe, or if we're retrofitting a mechanical seal, then we could put a new poison pad on the pipe. There's internal insulation parts which are fully encapsulated formed bolsters which are pinned and located in position to allow the movement to take place. We'll have a look at that in the next slide. And then we have a formed expansion joint. This is also a critical point I'll just cover in this application. When you see this picture here, you can see that the expansion joint is formed with a significant convolution. A flat expansion joint will crease up when the movement takes place. An expansion joint with a convolution will flex and not crease up, and that again will lead to a significant improvement in durability for cycles. Just to cover what these internal insulation parts might look like, this penetration seal is on a floor location with a high axial movement, a high amount of axial elongation, and you can see that the insulation, as we said in our secondary failure mode of a standard expansion joint, insulation gets compressed, and this causes hot spots to be developed as gas pass and heat comes through. You can see in that video just wanted to show you it again. You can see in that video that the insulation is not deformed at all. And this is also another standard DEKOMTE principle, that we want to make preformed insulation parts that insulate the correct area of expansion joint, allowing full function without a degrading effect by the compression of the insulation materials. So you can see there they're nicely interlocking as the movement takes place. Okay, the next solution which I'd like to touch on is from a completely different type of plant, conventional boiler, ash hopper expansion joint. These are significantly dirtier plants, a lot of ash and dust, and obviously at the bottom of the boiler we have all of that debris dropping down into the conveyor system. The traditional system is a water bath, so what we call a trough or a bath of water, that off the top of the bottom header there is a plate which dips into the water. A simple water seal that allows the boiler to drop down towards the floor and be sealed. Air ingress is the thing that we obviously don't want, because we want to optimize the combustion efficiency in these boilers, or rather you do, and therefore ensuring the sealing is in a good condition is quite key. You can see the picture on the left there. That's a typical sort of trough with a dipper plate. Obviously, because there's water, there's significant amounts of corrosion that takes place, both with the dipper plates. There is collision of the dipper plate and the trough and the boiler wall as movements on these old boilers becomes irregular. There's normally regular filling of water required. Most plants leave the tap on, as there is a significant evaporation and water spilling that takes place. Not only does corrosion take place of the water trough system that needs regular maintenance, but when water spills over the trough, we also then have significant maintenance and corrosion issues around the bottom of the boiler as well. So DEKOMTE's solution is to offer a fabric gas-tight solution. Here, the formed expansion joint again is a key aspect, because we want to avoid that we crease up the material as we have a significant vertical compression. Typically, we're looking at a compression in this case of between 200 and 300 millimeters for a typical 400 to 500 megawatt class boiler. Yeah, we're seeing that with that significant compression, the expansion joint life and the insulation parts are going to be quite key. I'll give a little bit of information here on some typical construction that we've done. We've done quite a number of these retrofits. Currently, there are 2 separate plants in the UK, 6 plants in the USA, and 2 plants in Germany where we've completed this style of retrofit. That was a small model that we made many years ago, where we demonstrated how this system worked, just how the compression worked and what happens in the deformation of those internal parts. Also discussing the ash protection internally. We need to leave in place the ash screen to give the maximum protection to the expansion joint, but we also have this internal flow shield which acts as a sealing and protective measure to close up the gap to the hopper wall at the bottom. Following on from that solution, we actually made some new solutions. The last 2 projects we've done in the USA actually are, we've changed the design slightly. And we changed the design because we actually recognized some of the installation aspects. Some of these boilers are of a significant vintage and therefore are not in let's say a reliable dimensional condition. When we take that cross-sectional dimension, we find that the difference can be 50, 100 millimeters out of squareness and out of parallel. And so we reconsidered how can the expansion joint be made to be easier to install and allow for more flexibility of the existing conditions. And therefore we just changed the expansion joint, really flipping it upside down slightly and considering a slightly wider scope. And the slightly wider scope is predominantly all on the top boiler connection side. So we now take the responsibility for the full connection because we recognise that most of the off-stand plates and off-stand steel work from the boiler header is not in good condition. So we want to replace all that. We also then have the flexibility of relocating it in the right position. We also change the expansion joint frame to give a longitudinal or radial flexibility of where that's located, because we don't want to force many hours of rework in trying to get that off-stand connection in the right position. So we've made an expansion joint which is a little more flexible to be able to have a bit more adjusting room on site. We've also changed some of the insulation parts, and you can see there's a tab insulation on the inside here under the flow plate, so that we also create an even better seal to the ash hopper wall. A secondary benefit, which I mentioned here, is the cladding issues. We recognise that the cladding and the external insulation on the header and the sloping tubes that come away from the header, although on paper they look fine, we realise, as is many the case when we visit a site, what you can draw on paper as perfect insulation system, when it comes to being executed on site, one, it's very difficult, and secondly, there will be problems with its attachment and its movement later on. So we wanted to allow a bit more flexibility that if the cladding and insulation system does fail, now it only falls onto the expansion joint frame and it doesn't actually impede the fabric parts themselves or affect the reliability of the fabric parts themselves. Okay, the last case study is just a boiler grate expansion joint. This is a really interesting location, probably one of the most complicated geometry expansion joints that we deliver. The principle of the expansion joint is straightforward enough, temperature and movement wise, but how it wraps around the bottom of the boiler and connects to the boiler grate means it changes direction, changes width, changes orientations of movements multiple times. And that again falls into one of DEKOMTE's strengths as a custom expansion joint builder, because manufacturing of a special formed shape which changes in geometry and perspective as it moves around the boiler is something that actually we can tackle as standard. We also see a point to touch on with this is that we see the difference again between OEM and retrofit. We've got experience of upgrading the original OEM construction. We're fortunate that we are in the UK and in Europe one of the main suppliers for waste energy plants as an OEM, but we are not advocating that the OEM solution is always in the best interest for the long life of reliability of the plant. And so we want to explain to some of these plants that actually there are options for improving the reliability by increasing internal protection, increasing the composition layers, improving that internal pillow construction, and also improving the external layers of the expansion joint, just to make them significantly more robust. It's again about a value analysis in this case, because the OEM is making the right decision for the product which will last the warranty period, the initial operating few years of the plant, whereas an end user may want to reconsider that they want a much longer durability and lifetime, and that definitely impacts on the product which we need to be supplying. On a big joint like this, we see it's very common to do patch repairs, and so that's also a point which I can throw in with this case study, that it's quite common to replace only certain section of expansion joint. And you can see in this case there's a spliced in part just to help the plant get to the next major outage. Some plants are luckier than others in that a short-term, what we consider to be a short-term patch repair ends up being a long-term fix. But I think for most we'd recommend that this be only a short or medium-term solution, and really a longer-term fix is going to be required. So just to pre-brief the Q&A session, I see we've got quite a few questions coming in, which we'll jump onto. But I just want to summarise by economic and value analysis, and that's quite important, that we consider the right solution, the right lifetime. I think it's important as a customer you tell us what's the lifetime that you want, and then we help you with what technical solutions there are to achieve those different lifetimes. We believe that the longer life product is going to be the most economical, but we can certainly talk with you about what the options really are. So let's just come to some of the expansion joints. Let's come to some of the questions. We've got a question. Firstly, does DEKOMTE offer expansion joints for hydrogen-fired gas turbine applications? Yeah, I'm sure many of you have seen there are a number of GT manufacturers now switching to hydrogen-fired. We actually have secured our first order from one of the major GT manufacturers for a pure hydrogen-fired gas turbine exhaust system already, but we have been supplying for several years to several gas turbines which are dual firing. I don't mean dual firing with oil and gas, that's already very old, but dual firing with hydrogen as well. So yes, there is some consideration impact of this. We see the temperatures in the GT exhaust increasing significantly, and obviously the choice of stainless material and that creep fatigue issues that need to be paid attention to. But in short, yes, we have some experience already of hydrogen-fired GT applications now. But if you'd like some more information, we can certainly give you a little bit more about what we've been doing to increase temperature resistance of the expansion joint. Second question, someone's asked about expansion joints suitable for over 700 degrees. Yes, that's also not a problem. Again, it's about the internal design. 700 degrees is an interesting number, purely because it's still possible to have a hot casing exhaust system externally insulated at that temperature. When we start to go above that, as we see in incineration plants or pyrolysis plants, approaching well over 1,000 degrees, then we start to need refractory or insulation line systems. So yeah, high temperature exhaust systems, yes. Another question, are expansion joints in this context considered to be last resort or secondary to piping design layout? Yes, good question. Of course, I would like to say that expansion joints are necessary in the whole piping system, but actually I agree with you. The expansion joint should be considered as a secondary point. It's better to get the piping design system right first. It's better to think about the hanger systems, vibration and damping systems first, and try to simplify the movement characteristics of the expansion joint. So to come to an expansion joint design which, let's say in a piping system which goes through a 90-degree corner, to put in 2 expansion joints, for example, could actually be better than putting in 1, because then the 2 expansion joints are purely coping with axial movement. So, but yes, piping system design is quite a key before we get to the expansion joint. Another question we've got is how do we perform thermal fatigue calculation, and does it always require CFD analysis? We have in-house capability for finite element and CFD. For thermal fatigue calculation, actually it's finite element really that is necessary rather than CFD. The CFD is useful in terms of how the temperature profile will work within the exhaust duct and how the heating up phase of the exhaust gas will take effect onto the seal. But it's more the FEA analysis which is key, which is how the temperature and stress will move across the frame during those transient conditions. Does it always need to be put through the computer analysis? I would argue no. I had a discussion with a customer only this morning where we tried to suggest to them that this has already been proven. We don't want to reinvent the wheel. So with all of the solutions that we already have installed, with all the references we've already got, I believe if we've already installed something of a similar nature, then why would we need to calculate it again? It's better we go and talk to that customer, visit that site, look at the installation, and see the reliability that's already been proven out. So most of the solutions we're talking about are already proven and therefore don't need additional analysis, but we're certainly capable and able, and there are definitely cases where new analysis can be really useful. Okay, another question we have is, could you touch on the membrane piping materials you would use for metallic bellows in the range of 600 to 800 degrees? Typically, metallic bellows will always be formed in stainless, so we're normally talking of 316 or 321 grade stainless materials. As soon as we're going above 600 or 700 degrees, that's when we're going to start to use some Inconel or Hastelloy based materials for even higher temperatures. The issue will also be about movement, because the temperature has an effect on the elasticity of this material. So if it's a very low movement, then a lower grade stainless could still be used because of the yield strength issues, okay? If we're in high temperature and the movement is high, then definitely we're going to have to look for some more exotic materials like Inconel. Thanks for the questions. Please keep the questions coming. We've still got a few more minutes and a few more questions here. Is the design life criteria calculation method for expansion joints and joints meant to absorb vibration differently? Yeah, vibration is a whole separate beast that needs to be considered. As I said earlier, vibration actually really impacts expansion joint life significantly. The other thing which impacts, as I also said, is the amplitude and the frequency. One other point maybe to consider about vibration is actually pulsation. If there's a gas flow or exhaust flow induced style of vibration, actually it's more a pressure issue than anything else. So yes, we can tackle these. They do need to be tackled slightly differently. So we might want to think about dampening the duct or installing some internal system within the expansion joint to tackle separately that pulsation or vibration element, and therefore tackle individually that subject against the gas membrane and gas tightness issue. Okay, we've got another question here about LP turbine applications. Someone's explaining they've got some circumferential cracking on multiple convolutions of a 3-meter diameter bellows with limited success and weld repairing. The convolutions are very close to each other with limited access. The material is very thin and difficult to weld. Yes, we would not recommend welding up metallic bellows. It's really against the whole design basis. If you weld up a bellow, you are now making it stiffer, which means it will now definitely either crack on the weld because it's not flexible enough, or it will crack in the adjacent convolution because you're putting too much stress of movement on the convolution adjacent. The replacement of the complete unit was extremely difficult due to size and access. Can these be replaced in multiple sections in 3 or 4, and how then could it be sealed? Yeah, as I said earlier, we can deliver, I touched on the penetration seals, we can deliver expansion joints in multiple parts, so what we call clamshell style. With clamshell style, you're limited to one layer. It's much better to have a multi-layer bellow. That's the most flexible environment, but to do it in multiple segments of installation, yes, you can have a single layer. So we just then need to be careful about, is the bellow going to be flexible enough? We can tune the bellows by convolution height, convolution density, and the material thickness. But that's definitely a challenge, I would say. So if you'd like to send us a separate note, or we'll follow up with you separately, the person who's asked that question, because certainly that's a little bit more complicated than just a yes or a no. Everything is possible, but you know, there are obviously then constraints to how to implement it. Another question, how do the expansion joints behave if there's a short-term pressure transient excursion which was in excess of the steady state pressure load? Okay, that's good. I did just mention that about pulsation. Pressure stability in the duct is quite important. However, we see on many different types of gas turbines, not to name any specific GT manufacturer, that directly at the GT exhaust there is a type of swirl that takes place, which when at the end of the diffuser we see the expansion joint has a negative pressure zone and a positive pressure zone. And during the different operating modes of the expansion of the unit, that pressure can change. So even though the specification refers to a static pressure to the duct, we actually already see on many gas turbines that is not really the case. So internal protection is quite key. If we talk about the specification, that the steady state pressure might be something like 50 or 70 millibar, maybe the way to try to answer this is, what is the capability of an expansion joint to resist 200 millibar? And the answer is yes. In most cases, the expansion joint is capable of somewhere close to double the original pressure that we're talking about on the drawing. Higher pressures, it will really depend on what the internal arrangement is looking like to see how much surface area, what force is being exerted onto the membrane, and therefore whether the clamping force of the expansion joint is sufficient enough to hold that pressure in. Okay, we've got one more question here. Are there any particular considerations when specifying expansion joints for applications on modern naval ships? So we're supplying expansion joints for diesel power generation and propulsion systems, and also gas turbine. There are naval, or in fact any sort of offshore environment, obviously there are significant considerations of material choice for corrosion. There's also considerable specification impact for what the real movement conditions are. I'd like to address a sort of secondary question really with this answer, that when we're talking about a specification and movement capability of an expansion joint, we often find that design engineers like to layer up contingency. So they might calculate that actually the expansion joint only thermally for the ductwork system is going to take 20 millimeters of movement. But they'll then say, well, we've got some wind loading, we've got some ship rotation, we've got some seismic load or any other contingency, which will impact to increase that to maybe 50 millimeters. They'll then say that, okay, we also need to allow additional tolerance for the construction of the unit and how all the equipment's going to be mounted, and so we're going to have an additional tolerance. What started off as a 20 millimeter movement, in the end, in the specification, it might say 70 millimeters. What's really important for us, and it's typical about this sort of marine application, is that we have an honesty in the specification with our customer, so that we understand what's the real thermal operating movement that might take place, and what are other factors of movements that might be required. And in that, we can then design the expansion joint that it can be installed with an installation tolerance, it can have a normal movement capability, and it can have an exceptional movement capability. And being a little bit more precise about how the specification plays out against the solution, I think is quite key. We're approaching the end on time, so I'll leave the other questions that have come in. Please, if you have further questions, write across to us. We'd love to support you in answering any of the questions you've got. I'd just like to close by saying DEKOMTE is always supplying a proven solution, and we'd love to help you in tailoring a solution specifically to the requirements you've got. I really thank you for your attention for the last hour, and I wish you all a very good day. Thank you very much.